the experiment that changed space travel forever. It began as a controlled test, carefully planned and quietly approved, with no expectation that it would alter the future of exploration in any meaningful way. The goal was modest, the risks were considered manageable, and the outcome was assumed to be incremental rather than transformative, the kind of experiment that fills technical reports but rarely captures imagination. To understand why this experiment still matters today, we need to revisit a moment when space travel was defined by rigid assumptions. Spacecraft followed predictable paths, relied on established propulsion methods, and operated within boundaries that engineers believed could not be crossed without unacceptable risk. Progress came through refinement, not disruption, and innovation was expected to move carefully within proven limits. That mindset shaped every mission that came before. The experiment was designed to test a single idea, one that challenged conventional thinking just enough to warrant investigation, but not enough to threaten existing systems. Engineers debated it cautiously, simulations were run repeatedly, and contingencies were layered into every phase, ensuring that failure would be contained and reversible. What no one fully anticipated was how the results would ripple outward. As the test unfolded, data began to diverge from predictions in subtle but undeniable ways. Performance exceeded expectations in some areas, while exposing entirely new variables in others, revealing interactions that had never been observed in operational conditions. The experiment was no longer answering one question, but raising many more. Slowly, a realization took hold among those watching closely. This was not simply a successful test or a failed one. It was a demonstration that the underlying rules guiding space travel might be more flexible than previously believed, opening possibilities that had been dismissed as impractical or unsafe. In that moment, an experiment meant to confirm limits instead began to dissolve them, setting the stage for a shift that would quietly reshape how humanity moves through space. As the implications of the results became clearer, discussion around the experiment shifted from technical validation to strategic reconsideration, because the data suggested advantages that could not be ignored. Efficiency gains appeared where none were expected, operational margins widened, and scenarios once labeled theoretical began to look achievable within existing constraints. Engineers revisited long-standing assumptions about propulsion, maneuvering, and mission design, realizing that the experiment had exposed inefficiencies embedded deep within accepted practice. Processes that were once treated as unavoidable costs of space travel now appeared optional, dependent more on tradition than necessity. The experiment did not introduce a radical new technology, but it reconfigured how known principles could be applied. What made the situation complex was risk. Adopting the findings meant stepping away from systems with decades of flight heritage in favor of approaches that, while promising, lacked extensive operational history. Spaceflight rewards caution, and the tension between innovation and reliability became a central point of debate. As discussions unfolded, the experiment's influence expanded beyond its original scope. Mission planners began incorporating its lessons into early-stage designs, exploring trajectories and timelines that previously would have been dismissed outright. Even modest adjustments began to compound, hinting at missions that could go farther, last longer, or operate more flexibly than before. At the same time, skeptics urged restraint, warning that enthusiasm could outpace understanding. The data was compelling, but incomplete, and extrapolating too far carried its own dangers. The experiment had opened a door, but stepping through it required confidence that the floor beyond was solid. In navigating that uncertainty, the experiment forced a broader conversation about how change is integrated into systems where failure carries extraordinary cost, and whether gradual improvement or bold adaptation truly defines progress in space exploration. The conflict reached its height as the experiment moved from analysis into decision-making, because acknowledging its success meant confronting the inertia built into space exploration itself. Established programs, funding models, and institutional expertise were all aligned around methods that had proven reliable over decades, and shifting away from them required more than data. It required trust in a future that had not yet been tested. Supporters argued that the experiment revealed a path toward fundamentally different mission architectures, where flexibility replaced rigidity and adaptation replaced brute force. They pointed out that the greatest risks in exploration often come not from new ideas, but from clinging too tightly to old ones as environments and objectives change. The experiment, in their view, was evidence that space travel could evolve without sacrificing safety. Opponents countered with caution grounded in experience. Space is unforgiving, and reliability is earned slowly through repetition. They warned that scaling an experimental success into full missions could expose weaknesses that only appear under prolonged stress, far from Earth and beyond rescue. The experiment had worked once, but history was filled with ideas that failed when pushed too far. This tension created a stalemate that extended beyond engineering. Political considerations, budget cycles, and public perception all influenced whether the experiment's lessons would be embraced or quietly sidelined. Innovation competed with accountability, and every decision carried implications that would echo for decades. What made the moment decisive was the recognition that refusing to act was itself a choice. By ignoring the experiment's implications, agencies risked locking future missions into constraints that no longer made sense. The question shifted from whether the experiment was perfect to whether the status quo was sufficient. In that realization, the experiment stopped being a technical milestone and became a test of vision, asking whether humanity was willing to let evidence reshape the way it reached for the stars. The climax of the story arrived when the experiment's principles began to appear quietly in operational missions, not as a dramatic overhaul, but as a series of deliberate choices that reshaped space travel from within. Techniques once considered experimental were folded into planning assumptions, altering trajectories, timelines, and margins in ways that accumulated into a lasting transformation. The resolution was subtle but profound. Spacecraft became more adaptable, missions more resilient, and planners more willing to question inherited constraints. The experiment did not replace established methods overnight, but it weakened the idea that there was only one correct way to move through space. Progress became less about following a fixed path and more about responding intelligently to conditions as they unfolded. Looking back, the experiment stands out not because of a single breakthrough, but because of what it permitted. It gave engineers and decision-makers permission to rethink fundamentals, to see space travel as a dynamic process rather than a rigid sequence. That shift in mindset continues to influence how new missions are conceived and executed. Today, as humanity prepares for more ambitious journeys, from extended lunar presence to deep space exploration, the legacy of that experiment remains embedded in countless design choices. Its impact is felt not in headlines, but in quiet efficiencies and expanded possibilities. Sometimes the changes that matter most are not the ones that announce themselves loudly, but the ones that redefine what feels possible. And in that sense, this experiment did not just change space travel, it changed how humanity imagines its future beyond Earth. Subscribe to join the journey.